Okay, Ricardo, now you can ask the question.
Okay. This is a more general question. So regarding the connection with the tight binding that was briefly mentioned. So if I have a crystal, and I mean the unit cell will have some sort of symmetries, some set of symmetries, and these symmetries will also be shared by the wave functions, so the Bloch wave functions. So if I try to approximate my Bloch wave function as a linear combination of atomic orbitals, just linear, there doesn't have to be, the coefficient doesn't have to be the plane waves. I will make it more general. So this is the orbitals are an orthogonal basis, so I expect that these procedures should be working good, should give decent results. So my question is, the orbitals that I choose to combine in principle doesn't have the same symmetries that my crystal have. I mean, and so I was wondering if these things could force put strong constraints on the linear coefficients that I choose, and if I can deduct these constraints without doing any calculations.
Okay, yes, actually, I'll be dealing exactly with that problem in a few slides, okay? From now. Yes, you know, that's an important point, and it will be even more important in our next lecture, where we'll consider topological aspects.
Yeah,
no, that's a very important point, but as I tell you, I'll explain it. If it's not clear enough, just
okay.
Yeah. Okay. Are there any other questions? Or?
I have like a small question regarding the exercises from the last lecture. But it's just like maybe a stupid question. Like in the last one, in the 3.4, like you ask for give like a graphic method to show that this like the C4 set plus and the mirror. Yeah, is the Cayley graph or
Yes,
it's just
basically, yeah, let me just show you on the blackboard. Yes, because that's why I forgot to explain that point. Let me see. So, okay, so I'll stop sharing. Okay, so can you see the blackboard now?
Yeah.
Okay, so I'll explain that very briefly. Yeah, I think that's what you say. Turn off the lights. For instance, for C4V, the idea is this. Remember, C4V has the 4 axes of C4C, yes, and then it has these planes, sigma, let's say sigma X and sigma Y. If I place this is the X axis and this is the Y axis, remember the mirror planes are perpendicular to the axis. So sigma X is perpendicular, is this here, and then I have the diagonals. Then that depends on the notation. In that list notation, this sigma dA, this sigma dB. Then this is the initial. I have an initial point here, and then I can see what the effect of all the elements of the group are on this. So, for instance, if I act with a 4-4 rotation, this goes to this point, then to this point, and then to this point. Okay. So I have act just with this, and from one initial position, I have found the other three. Now I can act, for instance, with sigma x on all of these results. Now sigma x acting on this gives me this. So just mirror this, this, and this. So just by acting with these two elements, I have obtained 1, 2, 3, 4, 5, 6, 7, 8. So it means that just by acting with these two elements, which are the generators, I have obtained all possible positions because the group only has 4 elements. So it only has 4 possible positions. And I have generated all the other things. For instance, all the other elements. You see, this is related to this by this reflection. Okay? This is related to this by this reflection. So the graphing method, the idea is the following. I mean, this is in Bradley's. In tables 1, you can find something similar, but it's not very much explained. So the idea is you want to make sure that any other operation in the group, I mean, the group has all these operations. You see, plus minus, sigma y, sigma dA, sigma dB. So the idea is that any other element in the group can be obtained by operating just with these two elements. For instance, let's assume that I act first with C4x, C4x, and then with sigma x. What do I get? This. You understand the thing graphically and algebraically. If I start from this and I act with C for Z, I go to this point. Now, if I apply this reflection, I end up here. But you realize that I could have gone from this to this directly by using sigma dB. So this is equal to sigma dB. You can check that any element in the group can be obtained by operating with these two things in different ways. You may have to take powers, for instance, C4C squared is C2C. So the generators are algebraic generators, okay? So that's the idea. I don't know, this is called a Cayley's, you mentioned diagram, or?
No, I was thinking of another thing, but yeah, that in the Bradley's and it's really clear. So thanks a lot.
Yeah, but that's what I mean by the graphic method, and this is very useful when you want to make sure that you're choosing a good set of generators. Because as we will see, many of the things, when you want to check, for instance, that the basis is correct and things like that, it's enough to check for the generators. You don't have to check for all the group, because algebraically, if something works for these two, since everything else is just an algebraic combination, it has to work. Okay, is that clear? Or
yeah, it's perfect. Thanks.
Okay, so well, let's begin with today's lecture. Then I'll be more time for questions. So today we're going to consider electron bands, see how we assign irreducible representations, see some of the implications, not all, and see what compatibility relations are. Okay, so now the first thing we are going to consider how we can make a tie binding model for graphene. Well, you know that graphene has two orbitals, I mean, has the carbon atom. This is the ground configuration. And the valence electrons are just these 4 electrons, because this is a core. These are core electrons. They are completely inert and they don't play any important role. So basically, for each atom, I have to consider 4 orbitals. One s orbital, and then the 3 px, py, pz orbitals. Okay. So this means that in each unit cell, I have to consider 8 orbitals. So if you are familiar with time binding models, this means that you will get a Hamiltonian, which is an 8 by 8 matrix. You have to diagonalize and you will find the 8 bands. Okay. Now,
sorry, are you sharing the slides again?
Sorry?
Do you share the slides again?
Oh, sorry. Yeah, I forgot. Yeah. Mm. Yes. Okay. So I was saying that this is the grand configuration for carbon. It has 6 electrons, but only these 4 electrons are valence electrons. These are core electrons, and they don't play a role. So if you want to make a tie binding model for the principal band in graphene, you will consider 4 orbitals per atom, up to a total of 8 orbitals. Okay, so you will have to diagonalize an A by A matrix, and you will find the 8 bands. Okay, I'll give you the result in a minute, but in principle, that's the idea. Okay, now you know that you will always use the tie binding model if you start from orbitals and you want to do it analytically or at least manually. And basically, what you do is you take combinations of these orbitals, and then you move into block waves. You could try to do the thing also directly in real space, but now the problem is much harder, because here you have 8 orbitals per unit cell. You have n unit cells, can be 10 to the 22, 10 to the 21, whatever, and you have to diagonalize a huge matrix. Okay, so that's the reason one goes into reciprocal space. I tell you this because next time we'll move back to direct space when we consider topology and topological quantum chemistry. Okay, but I mean, that's the normal procedure for a physicist. You just take linear combinations of atomic orbitals, 1 per orbital. So I will have a total of 8 block-like waves like this. They have this property, which you can show in one line, and that's that under translations, when I translate it, they just pick up a phase. So this means they are eigenstates of the translation operators. In other words, they belong to the irreducible representation tau k. Okay. Then block waves with different values of k. Here, by different values of k, I mean non-equivalent values of k. Remember that k was not momentum, was at best crystal momentum, but in fact, I mean, mathematically, this is just a label for an irreducible representation. And what really matters is this. Now, when I add a reciprocal lattice vector, this doesn't change. So it means that 2k's, if I can obtain one from the other just by adding a reciprocal lattice vector, they are the same. Okay, they are equivalent. So when I say different values of k, I mean non-equivalent values of k. That will be very important in a few slides. Okay, as we'll see. So they are not coupled just because they belong to different irreps. Now, the Hamiltonian must be a linear combination of bilinears, and I can only make bilinears when I take the same irrep. So if I consider a wave function and a wave function for a different k, I get 0. Okay, so basically, that's what I mean. So in this case, since I have 8 orbitals, I will get this A by A matrix, and this matrix will only connect wave functions with the same k. I mean, wave functions at the same point in the first Brisbane zone. Okay, that's what's really important. Okay, so instead of having this almost infinite by infinite matrix to solve, that is the problem in real space. In reciprocal space, I just have an NO times an O matrix to solve. So in this case, A by A matrix. Okay, and in fact, that's the result of a rather simple tie binding model with first neighbors and second neighbors. Okay, so up to second nearest neighbors. So you see that they are pretty good, especially from around the Fermi level and below. You compare this with the DFT computation, they are remarkably similar, even the values. Of course, I have adjusted some constants in the hopping intervals and things like that to get as close as I can to this. But tie binding models can be very good, even very simple tie binding models. The thing is not so good for the upper bands, but that's to be expected. Why? Because this is what people call a minimal atomic model. A minimal atomic model is when I just take the orbitals, the occupied orbitals. If I want to get much better than that, I should consider also 3s orbitals, even though they are empty. If I add them to the tie binding model, I improve it very much. But we are not really interested in getting some precise reproduction of this. Okay, so far this is just, I have just used the translation invariance in the sense that at each point in the Bridgewin zone I have to consider only block waves for that particular k point. Okay, since I only have a total of 8 waves because I have 8 orbitals, all these eigenvalues are obtained by diagonalizing an 8×8 matrix. So I get a total of 8 eigenvalues. Now I have considered at all the point group symmetry. When I consider the point group symmetry, we learn that these two things have to be degenerate, that these two things have to be degenerate, and things like this. Okay, so that's what we are going to do today. So to go beyond Bloch's theorem, I have to consider all the symmetries of graphene, not just the translation symmetries. Well, you can very easily see that if you take, for instance, this center, that this lattice is invariant under all these operations. Obviously, I can rotate this by 60 degrees rotations. This is this, by 120, by 180. You see, if I rotate, the lattice doesn't change at all. And always, I mean, atoms 1 and 2 are identical, but they are in different positions. Some of these operations take one atom 1 into one atom 2, like this, 60 degrees rotations. Others take atom 1 into atom 1. This will be important in very soon. Okay, but so far these are just symmetries. And then I have all these mirrors. These mirrors are, for instance, this is a mirror, obviously. This also is a mirror. I have a total of 6 different mirrors. And then in the next slide, I tell you exactly what these mirrors are. The sigma D's are these, sigma D1, sigma D2, sigma D3, and the sigma V are these 3. So a total of 6 mirrors. And you see that the lattice is perfectly symmetrical with respect to these reflections. So this, all in all, this is the group 3,6V, very similar to the group C3V that we've been studying. It's just I have more rotations and 2 sets of independent planes. Okay. Now there is another symmetry. Graphene is obviously invariant under reflections by the horizontal plane, by the plane of the sample. Okay. If I include sigma h, this means sigma means mirror and h horizontal, then instead of this group, this is double up to this is h with 24 elements. However, for many purposes, that's totally unnecessary. And that's the reason that most people that study graphene from the group theory viewpoint do everything just in terms of this group, which is easier because it has half as many elements. The reason is just this. The Hamiltonian cannot connect orbitals with different parities with respect to sigma h. Okay, so I have several orbitals, and when I reflect these orbitals, some orbitals change sign when I reflect on the horizontal plane, and some orbitals don't change sign. Okay, and they belong to different irreps of the total group of the 6H. They can never be connected. So as long as I remember this, I don't have to worry about this group, because the only effect of sigma h, at least when you are only considering the Hamiltonian, is that you have this kind of selection rule. The Hamiltonian that cannot couple different orbitals with different parities. In particular, these orbitals are even, and this is odd. Let me, I don't know if you remember this, let me, in 1 minute, I'll do it on the blackboard. So remember what an s orbital and p orbitals are. I mean, an s orbital is just any function of R. So it's a spherically symmetric function. Now, p orbitals are of this form. So these are purely radial functions, and this is just x, y, z. And so they are usually represented like this. If this is x, and this multiplication has probably this shape. And it's important to remember that this log is positive, is the positive log, and this log here is negative. Okay? Unlike an s orbital, which is just usually one considers that it's all positive, it doesn't really matter. Now, what happens if I consider the graphene plane? Etc. So my graphene is on this plane. The plane is xy. So if I have a Pc orbital, it's a Pc orbital. If I reflect this thing on this plane, it goes to this. So it changes sign. So the parity or the eigenvalue of the sigma h operation is minus. Okay. However, if I consider a sigma orbital, obviously this is spherically symmetric, nothing changes. So it has positive parity with respect to sigma h. And if I consider an orbital like this could be sigma x, sorry, px minus. If I reflect upon this line, nothing changes. So it also has positive parity. Okay, so that's how the sigma h parity works. Let's go back to this. So now, when I consider the tie binding model, these three orbitals are even, and Pz is odd. So this means that the Hamiltonian matrix doesn't couple at all the corresponding block waves that I construct from these orbitals and the block waves constructed from this one. So in some sense, I can compute independently the two bands that come from the two Pz orbitals. And these are called the pi bands, and they are by far the most important bands for the electronic properties, okay? Because this is the famous Dirac point, this is the Fermi level. And now I have these other bands, these are bonding bands, and these are anti-bonding bands. They are very important for the bonding of the atoms, okay? But they are not that important for transport phenomena because they are not very near the Fermi level, whereas the Fermi level gets very, very near to these two bands, which disperse linearly. This is the Dirac point, and all this ballistic behavior of electrons. I mean, an enormous amount of properties are related to the fact that this Dirac point in the band structure is right on at the Fermi level. Okay, so for the rest of this lecture, we are going to consider only these two bands, knowing that they are completely decoupled from the other bands. I'll give you one homework problem where you'll do the other thing. You'll do these three bands. Okay, and these are simpler. And for pedagogical reasons, I prefer to restrict myself for this lecture to these two bands. They are called the pi bands, and they arise. There are two bands because there are two Pz orbitals per unit cell, one per atom. Okay. Well, now I mentioned briefly at the end of the last lecture a very important concept, the concept of little group. What is the little group? Well, if I have a k vector, whenever I say the k vector, you can imagine a point in the Brillouin zone. The little group is the set of symmetries that leave k invariant. When I say invariant, it's invariant up to equivalence. So it means, it doesn't mean that the action of h over k leaves k identical, but the new k, the only difference with the previous, the original k is a vector in the reciprocal lattice. Why? Because then the two define the same irreducible representation. And for us, k is just a label for an irreducible representation of a translation group. Now, and this is a little group. I have all the elements in the space group, but a subset of these elements will leave any k that I'm given invariant. Okay. Now, if I consider the little group and I consider the corresponding block waves, since the little group cannot change k, the only effect of the elements in the little group will be to transform these waves among themselves. Okay, because it cannot change the value of k, so it can only change this. So this means that under the action of the little group, I have a representation of the space group, and this representation is called the small representation. Okay, so for each vector k in the bridging zone, I have a group, which is the little group, and I have a representation of this little group on the space of orbitals that transform according to k, and this is the small representation. So in order to understand all of this, first we'll have to see what are the little groups for different vectors in the bridging zone, and then we'll study the small representation. Why do we do this? Because the Hamiltonian, this is the Hamiltonian for a value of k. Okay, but remember that the Hamiltonian cannot connect different values of k, non-equivalent values of k. So the 8 by 8 Hamiltonian that we are considering must be invariant under the little group. So then I'm in a very similar situation to the one we were when we were considering the vibrational spectrum of molecules. The vibrational spectrum was obtained by diagonalizing the dynamical metrics, okay? And then we use group theory to see what degeneracies we have to have because of the dimensions of the reps. Now here, instead of the dynamical metrics, I have a Hamiltonian, which is k-dependent, just because I have a crystal, okay? But this Hamiltonian, this 8 by 8 Hamiltonian, has to be invariant under the little group. So this means that even though I have a space group, large group for the crystal, when I come to the task of diagonalizing and obtaining the Hamiltonian and obtaining the bands, I really only care about the little group. So the little group and the small representations are extremely important, much more important than the space group representations. Sometimes you really need the space group representation, okay, but these are usually more advanced applications, like when you consider electron-photon interactions, when you consider modulations of the crystal structure. But as long as you are considering bilinear operators, like the Hamiltonian, you only need to care about the small representations and the little group. So in the case of graphene, these are the high symmetry points in the bridging zone, gamma, k, and m. These are the high symmetry lines. I mean, usually people don't say high symmetry points, they say symmetry points or symmetric points, and symmetry lines or symmetric lines, okay? But they really mean high symmetry because this means that this has a high symmetry compared with any surrounding points on the bridging zone, okay? So which are the groups, the little groups? Well, for the high symmetry points, these are the little groups here. You are familiar with these groups in general. And for the lines, these are the symmetry groups, okay? So let's see if this makes sense. For instance, the gamma point is a vector with 0 length. Well, if I rotate a vector with 0 length, if I reflect, I always obtain a vector of 0 length. So obviously, gamma is always invariant under the whole group, okay? Here I'm just writing the point group, but it's also invariant under everything, okay? Now, if I consider, for instance, this line Obviously, if I take a vector that lays on this line like this, have a point here, and if I reflect it on this line, it's a mirror, this doesn't change. So, and that's the only thing that doesn't change it. Okay. If I rotate it by 60 degrees, it will come to this point, which is different, etc. So and the same happens here, and the same happens here. There is an exercise in the next problem set where you really have to obtain all these groups. I'm going to mention just this one because this is a bit strange. You see, this is the K point. C3b has 120 rotations. If I take this point and I rotate it by 120 degrees, I came up at this point. And this vector is very different from this vector. So what's going on? Well, what's going on is that when I mean that the K is invariant up to equivalence. So this is the K point. It's true that if I rotate it by C3b, it comes to this point. But now you can see very easily that the difference between this vector and this vector is just this vector here. And this vector is a vector in the reciprocal lattice, is V1. So K and this K here are exactly the same point when I consider this equivalence. In other words, the corresponding irreducible representation of the translation group is identical for this and for this. That explains something that may have puzzled you sometimes. People, when you see a representation of the bands for graphene, you see that there are Dirac points at these 6 points. Okay, this is the classical picture. And on the other hand, they tell you that there are only 2 Dirac points. Well, and the reason is that when one speaks of Dirac points, they have to be different in the sense of group theory, because that's the only thing that really matters. Now, this point, and these points are exactly the same point. This is K. This point, and this point are exactly the same point because they give rise to exactly the same irrep of the translation group, because the difference are vectors in the reciprocal lattice. Okay, so that's very important. When you're trying to find the little group, it's not the naive little group in general. You have to take into account this equivalence. Okay, is that clear? Any questions so far? So what if you do this, and you do that in one exercise, I think it's the first exercise, the problem set, you can find for all the symmetry points, gamma, K, and M, and for all the lines, you can find the symmetry groups with all the elements, okay? The way I have drawn this table, basically the 3 lines, each of the 3 symmetry lines connect 3 symmetry points, okay? So T connects gamma K. That's usually the way this is represented. Sigma connects gamma and M, and T primes connects K and M. So I have put here the line in between, okay? Now you can see, and we'll explore, we're going to exploit this thing a little bit later, that the little group for the line is always a subgroup of the little groups for the endpoints, okay, of the line. You see, these 2 elements are contained in this, and they are also contained here. And this is a general rule. The lines, the little groups for lines are always subgroups of the little groups for the endpoints, which are high symmetry points. Okay, this will be very important. This is related with subduction, and this is related with compatibility, which is crucial. The concept of compatibility is crucial for topological quantum chemistry and all the topological applications. So that's the reason I'm insisting on this. So at home, you should try to obtain this table here. Okay, this table, I mean, these elements are easy to understand. This, you should always look at this. to see what we are talking about, okay? To see what the mirrors really are. So you see that even though this is always C1H, the elements are different. In this case, for the line T is E and sigma V1, for the line sigma is E and sigma D2, etc. Okay. Well, now we go to another very, very important concept, which is the concept of Psi symmetry group. The Psi symmetry group is the local group that atoms really see and that orbitals in the atom see. And this is very much related with the first question today, the question about what happens with the orbitals. The orbitals, they are going to be deformed by the crystal field, well, all of this, okay? So the Psi symmetry group tells you what the symmetry, what kind of environment the atoms, the orbitals in the atoms feel. Now you see, graphene is really invariant under C6V, okay? The lattice is invariant under 6-fold rotations. However, if I live in this atom, my environment is not 6-fold rotation, okay? Invariant. Because you see, this direction is very different from this direction. In this direction, I have a nearby atom, it's a first neighbor. In this direction, this is a third neighbor. So the electric field, the crystal field that the orbitals are feeling, doesn't have at all the whole symmetry of the crystal. Well, this reduced symmetry is the Psi symmetry group, okay? Is the local symmetry group or is the environment symmetry. You can see that around this point, the invariances are just this. I mean, obviously this is invariant under 120 rotations. If I rotate around this point, 120, or around this point, nothing changes. And then this is invariant under this plane and this plane, but this is not invariant under this plane. If I reflect the crystal on this plane, this is not a local symmetry of this atom, okay? So this is very important. Why is this so very important? Because atomic orbitals are going to be distorted by the crystal field. And then this may lower the symmetry. How do we do that? Well, that has to do, I think it was our third or fourth lecture, where we studied subduction from the SO3 or O3, I mean for the full rotation group, to the Psi symmetry group. So an S orbital is an orbital that has zero angular momentum, is the zero, and that has positive parity, this is the plus. And this is an irrep of the whole rotation group, including reflections, inversions, and all these things. Okay, so this means that this is not really an equality, this is a subduction. Remember that you learn how to find the subduced representations by irreps of the whole O3 group. In particular, this subduces the A1. We did that for C3V, you may remember it. And this means that instead of the orbital S, when I'm in a crystal environment, I will speak of the A1, lowercase, orbital. Is there any difference between these two orbitals? Yes, there is a difference. That's the difference. The original S orbital has the full rotation symmetry. Now, this orbital is not spherically symmetric. It's no longer spherically symmetric because electrons are moving in a field, in an electric field, which is due to the neighboring atoms, and this is distorted. So that's the difference between S and A1. S is invariant under all the symmetries in the O3 group, in the full rotation group, including improper elements. A1 is only invariant under these elements, okay? And then you can wonder, well, then this is not an S orbital. Well, no, really. I mean, there is no way you can place an S orbital in a crystal. It cannot exist. you can place an A1 orbital. No, an S orbital immediately gets distorted. How can I get this orbital distorted if S orbitals are spherically symmetric? Because I get something which is called orbital mixing. When I place orbitals in a crystal, they immediately all mix up, okay, according to the irreps of the crystal field, the Psi symmetry group. To be more concrete, remember that when we studied subduction, we obtained this table. An S orbital becomes an A1 orbital. This, which would be degenerate, 3 orbitals, this degeneracy is partially broken, partly broken, and you get an A1, which is non-degenerate, and an E, which is a twofold degenerate, etc. Okay, and in fact, what happens that when I have an S orbitals transforms according to A1, but so transform under A1, Pz transform under A1. There is an orbital, a d orbital that transform under A1. There is 2 f orbitals that transform under A1, and under the crystal field, all these things get mixed up. Okay, so this is orbital mixing that always takes place, and in the case of configurations, you also have what people call configuration interaction, and that's extremely important phenomenon. And that's because when I lower the symmetry, I get many more invariants. So many matrix elements that had to be 0 because of the full rotation symmetry now can be non-zero. So there is a lot of mixing. So in what follows, we're going to study only the 2 bands arising from the Pc orbitals for spinless electrons. I can do this because this is the irreducible representation of the O3 group for the Px, Py, Pc orbitals, but this becomes reducible under the lower local symmetry group, under C3b. And this means that Pz and Px, Py decouple, okay? They are no longer degenerate, and I can study this thing independently of these 2 other things, okay? Well, independent to some extent, as we'll see. This is a very important concept because it's related to the most important concept probably in topological quantum chemistry, which is the concept of elementary band representation, EBR. Okay, we'll see that this gives rise to an EBR and this gives rise to another EBR. In this case, for practical purposes, P decomposes into A1 and E. A1 is related to Pz and E is related to Pspy. Since we are interested only in the P1 Pz orbitals, we just consider A1. Okay, so now I have to place these A1 orbitals at all the atoms. Okay, and that's what I have. So you see, they are not really Pz orbitals. I mean, you should understand this thing as a cross section of a Pz orbital. Just remember in your, I mean, remember that a Pz orbital has 2 lobes. One lobe goes up, is above the plane of the honeycomb. Another lobe, the negative lobe, is below, underneath the plane of the honeycomb. If you take a cross section of the lobe above, for instance, you get this. The same for the others. It's very easy to understand this distortion. Remember that electrons interact with each other. So the electronic clouds have a repulsion because they are negative clouds. So due to this repulsion, well, the orbitals are deformed. So well, even, I mean, people usually don't make this point when they say, I have constructed a tie-binding model based on p orbitals, d orbitals. That's never really true. Okay, they are always orbitals, tie-binding models based on irreducible representations or crystal orbitals, even if they don't say it. Okay. So let's stop for a couple of minutes. I have to take more water and then we continue. Okay, any questions so far? Okay, let me point out that how important this really is. I mean, this seems something almost anecdotic. Okay, yes, the orbitals are deformed, so what? Well, it's very important for the following reason. When you consider nearest neighbor interactions, hoppings, for instance, you know that if you have ever constructed a tie binding model, the most important parameters are the hopping parameters, which is just the tunneling probability of an electron going from this orbital to this orbital. Okay, for nearest neighbors, it's obvious that these three hoppings are identical. Okay, when you consider, and this is true if they are s orbitals or if they are a1 orbitals. Okay, however, when you go beyond nearest neighbors, you may have problems because, for instance, do you think if you think that you are really working with s orbitals, you would say, well, the hopping depends only on the distance because s orbitals are completely isotropic. However, these things are not isotropic. So you see that the relation between this and this, or you have these things are pointing to each other, is very different from the relation from this to this. Of course, they are also at different distance, but they are different because here you have these two things pointing to each other and you don't have anything pointing to each other. So these things are not as isotropic as they are the s orbitals. So what is the practical consequence? The practical consequence is that if you think that you are working with s orbitals, usually your tie binding model is going to have fewer independent parameters than if you are aware that you are working with these distorted orbitals. In other words, if you don't really need group theory to construct a tie binding model, but if you do, you always risk the following thing. You may leave out couplings, which are forbidden if these are really s orbitals, just by symmetry, because you have a higher symmetry, but they are allowed when you take into account that these things are not so symmetric, there are only A1 symmetric orbitals. And this happens once in a while, that somebody constructs a tie-binding model. This time-binding model is not the most general model allowed by the symmetries. And some of the conclusions, for instance, some degeneracies, are really artifacts of the fact that you are leaving out couplings which should be there. So the only way that you can be sure that you are constructing a good tie-binding model is by knowing at least some group theory, so that you don't leave out couplings which are allowed by symmetries, okay? And that's very important when you study properties, when you study topological models. You have to make sure that you really construct the most general Hamiltonian, because otherwise you will leave out phases, or you will reach out conclusions which are wrong, because some degeneracies that you say are there, they are not there, things like that, okay? So you have these orbitals, these green and red orbitals, and now you form two different types of block waves. One is based on the green orbitals, the other is based on the red orbitals corresponding to the two atoms, okay? So these are distorted Pc orbital. So these two block waves, at any point in the first bridging zone, transform under the corresponding little group, because since the little group doesn't change K, the only thing that it can do is that this becomes a linear combination of these two. The corresponding 2x2 matrices are the two-dimensional representation that we are going to call capital T sub K. So at each point in the bridging zone, there is a two-dimensional representation. Also, at each point in the bridging zone, there is a 2x2 Hamiltonian, which is the Hamiltonian that couples these two wave functions. Remember, there are also another 6 wave functions, but since they have different parity with respect to mirror reflections on the sample plane, they are completely uncoupled. Okay, so our problem is just like a 2x2 as a two-dimensional Hamiltonian, and there is a two-dimensional representation. And basically, what we are going to do next, we are going to decompose this representation into representations of the corresponding little groups. Okay, and to do this, we must compute the character. So how do we compute the character of this two-dimensional representation? I mean, this two-dimensional representation tells you how these two wave functions transform. Well, I give you the recipe, and then I'll try to argue that this is correct. But if you think long enough about it, you will find that this is correct. You have to think a lot, maybe 10 minutes or so. This is the recipe to compute the characters of this representation. We could call it the electronic representation, because that's the way electronic block waves transform. It doesn't have a name, okay? Well, this is the recipe. This thing here is equal to 1 if the atom I is invariant under G, 0 otherwise. Invariant means the following thing. Means that if the atom is type 1 atom, the symmetry takes you into a type 1 atom. That means to be invariant. It's invariant up to translations, okay? In the same way that the little group of the vector K is invariance up to translations in the reciprocal lattice, okay? We'll see this in a practical. I have to give you the recipe, but when you see it in practice, it's very simple. This phase may arise due to the fact that we are rotating or transforming block waves, and block waves carry phases. They are like very close to plane waves, and they carry phases. So this is a phase that may arise, and this phase depends on the group element, and the K will compute this in detail, so you will see what this is. And this is the character of the irreducible representation of the orbitals, okay? In this case, the Pc orbitals transform under the A1 representation of the local symmetry group, of the Psi symmetry group. So for these orbitals, these characters are always equal to 1. So this is very simple. Okay, so I'm going to argue now, just very quickly, why we get this formula. Basically, you have to remember that we had a very similar problem when we consider the vibrational representation or the mechanical representation in molecules. What was the problem there? We had several atoms, like for instance, for the methane, and some of these atoms were exchanged by the symmetries of the group. For instance, the 4 hydrogen atoms in the methane molecule were exchanged among themselves by the TD group, which was the group for the methane molecule. Okay. Now, at each atom, I had 3 displacements: the X, Y, and Z displacement that transform according to the V, the vector representation. And then that implied that the mechanical representation had a block structure. I think we saw that at the 2nd or 3rd lecture. I don't remember exactly. You should go back to that. Okay. So the fact that this had a block structure, I mean the vibrational representation, means that if we want to compute the character, I mean the trace of the mechanical representation, we only have to care about blocks that are right on the diagonal. Because when you have a block which is not on the diagonal, does not contribute to the trace. Now, for a block to be on the diagonal, what I need is that the atom, the corresponding atom, is invariant. So that's the origin of this thing here. So I only count one atom or one orbital if the corresponding atom doesn't change when I rotate it. It doesn't really matter if it changes to a different atom, but an equivalent atom, type 1, because remember, block waves are linear combinations of all the type 1 atoms. And here we are seeing how block waves transform. So it doesn't really matter whether it takes you to exactly the same atom or to an atom which is of the same time, but at a different point in the lattice. And this may give rise to a phase, and that's the reason there is a phase here, okay? In the case of molecules, the formula which was the equivalent of this one was this. Remember, the character of the mechanical representation was the character of the vector representation times the number of invariant atoms. Why? Because the displacements that I place on each atom transform according to this representation, so I need this character. Now, in the case of electrons, the orbitals that I place at each atom transform according to their irreducible representation, in this case, A1. And now, in this case, there were no phases. So I just had to multiply this was the same for all the atoms, to multiply this by the number of atoms on the diagonal. In fact, that's what happens here if the phases are trivial. When the phases are trivial, the sum of their atoms with this function, which is 1 only for invariant atoms, is the same as multiplying by the number of invariant atoms. Okay, so this is roughly the justification. The only thing that changes is that instead of the vector representation, I can have any representation. In this case, is the A1 representation, and that I have phases. I cannot have phases on a molecule because there are no K vectors, there are no waves. Okay, a crystal can be understood as a giant or as an infinite molecule, and in that case, I have phases also. So, well, let's try to construct this representation for the gamma point. In this case, I mean, at the gamma point and for all these points, the character is always 1. So I can just forget about this. When you do at home the px and py orbitals, this will be the character of the E representation, and you cannot just get rid of this. Okay, but in this case, we don't care about the character because it's always, the trace is always 1. Now, since there are no traces, I mean, since there are no, at the gamma point, K is equal to 0. So the block wave doesn't have any phase. I just take a linear combination of all the atoms, the orbitals without any phase. So if I move from one atom to the other, the phase is always the same. So there is no phase. So this means that this just becomes the number of invariant atoms, because this is 1 for the invariant atoms and 0 for the non-invariant atoms. Okay. So in this case, this is very simple. All I have to do is for each element of C6V, which is the little group for the K point, see how many atoms are invariant. Obviously, under E, the 2 atoms are invariant because I don't do anything. Under C3 plus, remember, I always rotate around this point, 1 goes to 1. So in that sense, it's invariant. So there are 2 invariants. And the reason is that in that sense it's invariant is that the block wave has this atom, so I'm just changing from one atom to the other in the block wave. But that's the same block wave. There are only 2 block waves, one based on one atom, the atoms 1, and another block wave based on atoms 2. So it's the same block wave. So that's invariant. C2 takes 1 into 2. So this is not invariant. The same is true for C6. However, C3 takes this into this, which is equivalent, etc. Okay. When you remember this plane, and this plane, which are the CD planes, take 1 into 1, 2 into 2, so I get a 2, etc. So it's very simple in this case because there are no phases. Okay. So all I have to do now is this representation. I have to decompose into irreducible representations of the group C6V. Basically, these are the irreducible representations according to your tables. So I have to look at this. And then, well, just by using the magic formula or just by inspection, I realize that this is equal to A1 plus B2. This is A1, this is B2, and as you see, if I add these 2 things, I get exactly these characters. Otherwise, if you cannot guess it, just use the magic formula. However, when you are considering space groups, when you are considering crystals, the usual thing is not to use these labels, but to use these labels, just numbers. That's the most common practice. This practice wasn't followed in the paper that I showed you, the DFT bands, but the most common practice is to just, instead of using these labels, use these labels. If this is the gamma point, just like this, for the gamma point, when you are at a different point, like the K point, you have to substitute K for gamma. So instead of, if this were the K point, you will write K1 plus K3, etc. Okay, so you'll see that in a minute. So what is this telling me? Well, this is telling me that the Hamiltonian, the 2 by 2 Hamiltonian at the gamma point has 2 non-degenerate levels. Why? Because both gamma 1 and gamma 3 are one-dimensional representations. So the 2 bands at the gamma point cannot be, or in general, degenerate, because these 2 reps are different. I mean, they might be accidentally, but the probability is 0, as I told you. Okay. So in other words, they are not degenerate. So the 2 bands at the gamma point are not degenerate. Okay. And I have more information. They transform according to these small representations. This is important, for instance, if you are studying Raman spectroscopy and things like that, because there are selection rules depending on these things. You might have transitions for some IREPs and not for others. For us, identifying the IREP contents is going to be extremely important in our next lecture in order to find the topology of the bands. Okay. Any questions so far? as I tell you, I mean, I really recommend that you do the problem sets, the corresponding homework, because you'll have to do this for the px and py orbitals. It's a bit more involved, but then you will really understand everything. So let's go to the K point. Now the K point, I mean, the wave vector is different from zero, so there might be phases. I have to keep the phases. Still, the irreducible representation of the Psi symmetry group is A1, so it doesn't matter. I mean, there is no, the character is 1, but I have to care about invariance, and I have to care about phases. And in fact, in this case, when you do compute the phases, you find non-trivial phases. See, here I'm representing together the product of this product. Why? Because when the atom is not invariant, there is no point in computing the phase, because after all, the contribution to the character is the product of the phase times this theta function, and this theta function is different from zero only if the atom is invariant. So never waste your time computing phases for atoms which are not invariant, okay? So that's the reason I represent here just the product. You see that under C3, if I rotate around this point, 1 goes to 1 and 2 goes to 2. So both are invariant, but have different phases, okay? These things may also have phases, but we don't care about them, because even if this is non-trivial, this is 0, so why waste time computing them? So in the next slides, we are going to compute these phases, okay? Because this is a bit tricky. The reason we have phases is because I'm taking linear combinations of the orbitals placed around different atoms, and the linear combination carries phases which depend on the unit cell the atom is in. Remember that T was a vector in the Graphene lattice, on the direct lattice, and this is a vector that goes from the origin to the origin of the corresponding cell, okay? So the phase depends only on which cell the atom is in, okay? This is the unit cell. So you see, for instance, that this atom and this atom are in the same unit cell. The next unit cell will be here. So this atom and this atom are also in the same unit cell, but this is a different unit cell. So it's going to have a different T, they are going to have different phases. So basically, we should examine the phase for each of the atoms in the lattice. But there are infinitely many atoms, so it's a bit hard to do. And in practice, since we are rotating things around this atom, this point, this is the origin of the direct space, we are only going to use or to consider symmetry operations around this point, like rotations, mirror planes, things like that. It is enough to study the phases for these atoms, okay? It's a very instructive exercise to obtain the phases for other atoms and see what patterns you find, and it's amusing. But if you just want to compute the phases in the previous formula, you just have to consider this hexagon of atoms and see what happens with the phases when I rotate the crystal or when I reflect the crystal. So in the next slide, I'm going to represent exactly these 6 atoms. Also, it's very important to use the coordinates using these vectors. Why? Because this is a kind of orthogonal basis. Okay, so it means that the translations should be given as linear combinations of these unit vectors. I mean, not unit, but these primitive vectors. And also the coordinates of the different points in the bridging zone should be given as linear combinations of these reciprocal lattice vectors. So it's not good to use the ordinary Cartesian coordinates, because then you have a lot of angles and complicated things. And these things are constructed. This is the primitive vectors. These are the reciprocal primitive vectors with this orthogonality condition. So it's very easy to work. So for instance, it's important that you realize that the K point is given by this linear combination of V1 and V2. It's that easy to see. This can, I mean, you have to use a little bit of trigonometry, but this is exactly at 2/3 of V1. I have to project like this, and I have to project like this. And this is 1/3 of V2. I mean, I have to project always parallel to the vectors, right? So the coordinates. This is what people call contravariant coordinates, okay? If you project normally, then what you find is the covariant coordinates, which are entirely different and have no use in group theory here. Okay, so is that clear? So these are our ring of 6 atoms. You see that the 6 atoms belong to 4 different cells. The origins of the cells, which that's what enter here, are obviously this. This is the 0, 0, -1, 0, -1, -1, 0, -1. Okay, it's obvious because we are using as basis vector this and this. So the coordinates of this point using this vector and this vector are given by this. Now the K point, I know the coordinates are 2/3 and 1/3. So you see that the phase, if in terms of M1 and M2, which are given by these numbers, and the components of K1 and K2 are just given by this very simple formula. That's the advantage of using primitive vectors instead of the ordinary Cartesian vectors. You should never use Cartesian vectors to compute phases. It's a mess. So now immediately you see that the phase for this cell is 0 because M1 and M2 is 0. So, I mean, this is 0, so the phase is 1. So if you do this thing, you can do this at home for the 4 cells. These are the phases. So this means that when I consider a block wave, a block-like wave, at the K point, this atom carries a phase of 1. These 2 atoms carries a phase of omega star in the complex conjugate, and 1. Okay, and now I can see what happens with these phases when I rotate this, when I reflect, when everything. I'm going to do it just for the C3 rotations, because all other operations don't leave the atoms invariant, so we don't have to care about that. Okay, so just remember, we are going to consider a block wave based on atoms of type 1. So this will carry phases. This will carry a phase 1. This will carry a phase omega, and this will carry a phase omega star. Exactly this. Okay. And now I'm going to rotate this by a 120-degree rotation. So if I rotate, this atom goes to this point. So now this phase is 1 instead of omega. This goes to this point. So this phase is omega instead of omega star. And this goes to this. So this just exchanges the phases. So this, I know that is still the same block wave because K is invariant. It doesn't look like the same block wave, but it's the same block wave. In fact, it's the same block wave by multiplied by omega star. Okay, so this is the phase. When I rotate this thing, this is a block wave at the K point. That's still a block wave at the K point, but multiplied by this phase. Why? Because you see omega times omega star, times omega star gives you 1. Omega star times omega star is omega star squared, that you can check that this is omega. And omega star times 1 is omega star. So you see, when I rotate this block wave, it picks up a phase, a non-trivial phase, which is this one. It's still the same block wave, but with a phase. Well, you can do exactly the same thing for the green atoms, the 2 atoms of type 2. and you get just this phase. You can do this at home, okay? So this explains the omega star and omega phases here, okay? And whenever you work with electronic bands, you may have to do this, okay? You may have to compute phases. The same is true for phonons. I mean, whenever you work with block waves, you have to care about the fact that when you transform a block wave, maybe you can get the same block wave, but sometimes you can get multiplied by a non-trivial phase. Okay, so I just have to add, remember it was a sum for the character, so 1 plus 1, 2. The sum of these two numbers is -1, as you can see easily, and this is 0. These are the irreducible representations of the little point group. The little point group is C3b. You have to use these as labels. So you immediately find that this corresponds to this. E is the label considered as a point group, but considered as a space group. It's better to use these labels, but instead of gamma, you have to use K, that's the convention. So this is K2. And now this is giving you very important information. Since this K3 is two-dimensional, you know that at this point, the two bands necessarily have to be degenerate. And that's the origin of the Dirac point. It's just a consequence of the symmetry. Okay, this doesn't tell you that you really have a Dirac point, because Dirac point, to have a Dirac point, I mean, this only tells you that they are degenerate. Still, you could have quadratic dispersion and things like that. So you have to go beyond this analysis, still using group theory, but it's slightly more sophisticated than the analysis here to show that this is a Dirac point, okay? But okay, that's a little bit beyond the scope of this course, okay? You have to learn a little more group theory to really show that the thing is really a Dirac point. So the fact that K2 is two-dimensional implies the degeneracy of the two bands at the K point. Well, you can do the same thing at the end point, and you get this. In this case, at the end point, these are M1 and M2 are one-dimensional, so you know that they are not degenerate, okay? Now you can proceed to do the same thing with the lines. For lines, the computation of phases is always almost always unavoidable, and it's a bit more complicated here. But you can completely avoid repeating the analysis for the lines if you use subduction. That's the power of subduction. I'm going to do this just for one line. And basically, I'm going to do it for the T line that connects gamma and K. And now you realize that this, and if you think a little, you see that this has always has to be like that. That's the little point, the little group of the line is a subgroup of both the little groups of the gamma point and the K point, okay? So if I know the irreps for this group, I can just immediately use subduction to find the irreps on the line, okay? Or I can also do it from K, and I should get the same result. That's where compatibility comes about. Everything should be compatible. So I'll do it for this line, and you can do it at home for all the other lines. Well, the idea is just quite simple. Here I have the irreps of the C3, I mean, of the gamma point, and which is C6V, and of the T line, which is just C1H, okay? Previously, I knew how these things were connected, okay? So I have this point group and I have this point group. So the idea is that any irrep of this big group is going to subduce any irrep or linear combination of irreps, sum of irreps for this. How do I do it? Just by identifying the two things. So, for instance, this only has two elements. It has the identity and a mirror plane. This mirror plane, one has to be careful, is not any mirror plane. It's exactly the CV1 mirror plane. Okay, you do this just by looking at the region zone. So this is from the original representation. I only care about this column and this column. To see the representation subduced at C1H, I only care for these two elements. So if I look at all these columns, irreps are subduced by each of these. Since I'm only interested in computing this line, and the only irreps that appear were gamma 1 and gamma 3, I only have to care about gamma 1, which is 1, 1, and gamma 3, which is 1 minus 1. So comparing this with this, I immediately see that gamma 1 subduces T1, and then gamma 3 subduces T2. Okay? These are called compatibility relations. I mean, the subduction relations between the little groups of high symmetry points and the little group of the connecting high symmetry lines are called compatibility relations. Okay, because they impose a lot of compatibility constraints, as we'll see in the next lecture. Is this clear? So if you have done the exercises where you have to subduce and you look at the slides, probably you understand this. If not, well, can always what we did in that previous lecture, and you'll see that this is really very simple. And you can do this for all the lines and for all the subductions. So we have obtained this decomposition of the representation for the gamma, this is what we have obtained explicitly, the decomposition of the gamma point. But now, since we have these subductions, we immediately know the decomposition at the T lines. Remember, that's what we did with the molecules. Since we knew the decomposition of the vibrational representation for the methane molecule, we could use subduction to compute the mechanical or the vibrational representation for the deuterated methane molecule without doing anything, just by using the compatibility relation. Okay, and that's what one usually does for the lines. I mean, nobody studies the lines explicitly, just use subduction. So you can do that in the same way, all the other subductions, and you'll do that in an exercise at home. It's very simple. And then from these decompositions at the gamma, K, and M points that we already knew, we immediately find the decompositions at the lines. You see, there is compatibility in the following sense. The line T connects the gamma point and the K point. So I can use subduction from either point. If I use subduction from the gamma point, gamma 1 subduces T1, gamma 3 subduces T2, and I get T1 plus T2. But if I use subduction from K, K3 subduces T1 plus T2. So I already get T1 plus T2 immediately. And the same is true for all, I mean, a line always connects to high symmetry points. So there are always two different ways of using subduction, and they should always give the same result. If you get different results, there is a mistake somewhere. That's the nice thing about group theory, that usually any mistake that you make immediately, you can track it because something gets wrong. I mean, something, you get some impossible result, like fractional multiplicities and things like that. Okay. So that's the end of our computation. Now we know how these two bands, what representations are involved at all the points. At the high symmetry points, you have gamma 3 and gamma 1. Here you have K3, and here you have gamma 3 and gamma 1. Gamma 1 and gamma 3, M2 and M1 are one-dimensional, so that's the reason that the bands stay non-degenerate at these points. But here K3 is degenerate, so they necessarily must cross at this point. This is what people call a symmetry protected or symmetry enforced crossing or degeneracy. Okay, and now you can complete this thing with the lines. Okay, this will be extremely important when we consider the topology of the bands, and it's also very important if you want to consider optical transitions between different bands, things like that, because there are, I mean, you can use the machinery of group theory to find selection rules, and you may know that maybe this is allowed, maybe this is allowed for an optical dipole transition, but it's not allowed for a magnetic dipole, etc. So this contains an awful lot of information. We are not going to exploit this information for transitions, for optical transitions, of non-radiative transitions, like can you go from this to this by absorption of a phonon, things like this. You can answer all these questions just by knowing these labels and knowing some group theory. But basically, we're going just to dedicate this lecture to see the topological implications of these assignments. Okay. Now, something very important. You see, I'm assigning gamma 1 to this lambda, to this band, and gamma 3 to this one. Could be the other way. I mean, just from symmetry, I cannot tell which is which. Of course, there are some compatibility relations, but there is an ambiguity, and the same is true here for M2 and M1. Could go the other way. In this case, I have actually constructed a model, a time-binding model. I have solved the model, and when you solve the model, you also have the eigenvectors. And if you have an eigenvector, you can identify the symmetry of the eigenvectors. And that's the reason that I know that this is gamma 1 and this is gamma 3. But you could change this by changing the couplings in the model, the hoppings and things like that, or maybe not. I mean, that's something one has to study carefully. But that's the end of today's lecture. So if you have any question.
Okay, if there are no questions, we close the session. And remember, next week, there is no group theory lecture. We will reconvene in the 30th of March, on the 30th of March. Okay, so it's 2 weeks from now. So if you really want to profit from this lecture, I recommend that you try to go through all the previous slides and you try to do as many exercises in the slides as you can, because I mean, next lecture is quite involved, deals with topology, and it relies on all the concepts that we have developed so far. And so if you really reproduce this and you do the same thing for the sigma bands, then you will follow much better the lecture. Okay, even if you don't, you will understand part of it, but not as much. Okay, so then see you in 2 weeks. Bye bye.